Okay, dynamic latch, the quite old one has a static power consumption with the input transistor paired with the latch. You see here, this is latch, right? Inverter, cross-coupled, right? But nowadays we use only dynamic latch. But well, because of this positive feedback, right? As you know, the small signal difference at the initial will be exponentially increased, right? So at data converter, at a given time, we need to generate a logic level signal difference. So positive feedback is needed, not high gain amplifier, right? High gain amplifier is not proper. So if we solve the small signal model of this inverter, then we can find this. Oops, sorry. We can find where is it? The output voltage behavior, which is positive exponential, right? As time goes, it develops exponentially. And then as it reaches VDD or ground, then amplifier, I mean, inverters are not the amplifier anymore. I mean, the gain will be reduced, right? So they will saturate like this. So what we need to check here is that the time constant is determined by C1 over GM. So for fast settling, we need small capacitance and large GM. This is quite understandable, right? If we have large cap here, then when we drive the cap with the finite current of the GM cell, inverter can be thought of as a GM cell, right? Then it takes a longer time. And well, we need to have larger GM to drive the load fast, right? So in order to reach to a certain level, the time required reaching to a certain level is a log function of the 1 over initial voltage. So as we have a very small initial voltage, then time to generate the logic level output difference that can require quite a long time, which is called metastability, right? Okay, as I mentioned, so earlier we have utilized like latch in parallel with input pair. Latch is enabled only when the switch is turned on, but because of this parallel path, anyway, during the half clock cycle, we have a steady current. But in 1995, like about 30 years ago, people decided to stack the input pair with the latch. So input pair and latch, right? This is for latch enable. Then we have only dynamic power consumption, because when the latch generates like output plus and minus, then well, this PMOS will be turned off, and because of this falling signal, this one will be turned off, right? So we are not going to have a static current path, so we can reduce power consumption. Only when we generate the positive feedback, we consume dynamic power. And dynamic latch is quite again dynamic circuit. So at the beginning, if we take a look at the circuit operation, then for clear reset, we will reset this node as well during the reset phase. Then this node will be also reset by this switch. So initially, the latch's output is reset to VDD, and latch is, can you say input here? Because this differential pair gives a signal to this side, right? So input is also reset to VDD, right? And then when the latch is enabled, the PMOS switches will be turned off, and this tail current source will be turned on. So at the beginning, what needs to be done first is to discharge these capacitors, which are initially charged on to VDD, right? Then signal dependent, well, let's say input P was large and the input N was smaller, then more current and smaller current will be there. So this one will discharge first. Until when? This one reaches VDD minus threshold voltage, then this one will be turned on, right? So which one turns on first makes the decision, polarity decision. So for example, if we have here a larger capacitor than this one, then actually this one works as an offset. Even if we have the same current with the same input, if we have larger capacitor here, because this one's voltage will increase slowly, so this one will turn on first. So let's say this one's gonna discharge first, the output node, then this one, right? So this makes offset. Unlike a static circuit, because the dynamic amplifier works current capacitor discharge manner, any parasitic difference will make an offset. For example, like this node, we have cross-coupled connection, right? But when we lay out this connection, we cannot avoid parasitic mismatch. So here and here, we are very likely to have different parasitic. Metal layer will be different, right? Pattern will be different. So those will work as an offset. That's what I wanted to mention about this one. And then when after these guys are turned on, then the output node voltage will discharge, which turns on the PMOS transistor, right? So at first the output will discharge, and then when PMOS turns on, let's say if this one is turned on first. Then while the output voltage discharges here, this one turns on more stronger, right? So this one pour the current. So make the output voltage, because of this one, the output voltage actually increases eventually, right? And as this voltage reduces, this one turns off, right? This one it goes to be turned off. So this one's current reduces and this one's current increases. So eventually this one goes there, and this one works oppositely. So the latch, when PMOS turns on, we have latch, right? Because inverter turns on. So it works like this. And well, in this configuration, we can think the differential pair as a preamplifier for the latch, right? We are amplifying the input signal by discharging the capacitor, right? Until when? The voltage here again reaches VDD minus threshold. After that, the voltage will not change that much, right? For a while. So in order to tell this one's gain, preamplifier gain, we can think of this one as a kind of preamplifier for the latch. To calculate gain, we need to find the time when this one, the node voltage, reaches VDD minus threshold voltage. So, GM green difference, the current difference will charge the capacitor difference. The two capacitor in differential manner, right? And when time and as this is discharging circuit, the output voltage will time varying, right? As we discharge more, the output difference will be developed more. But the thing is that when the voltage here reaches a threshold, VDD minus VTH, then it stops. So the time we have gain will be like this. With the when the node voltage here is discharged with this current by this much threshold voltage, then we have just the maximum gain there, and then gain will not change that much. Okay, so by putting this time here, we can calculate gain, and the gain can be found like this. As we have a smaller kind of current through the transistor, and as we have a larger GM, and as we have more voltage drop, then we can develop more output signal, right? So the gain will be determined like this way.